Hello dear students, today we will start the topic that is on ECG signal processing. We have seen the different waveforms or different parameters that are there in ECG signal, and in this lecture we'll see how we can process the ECG signal to remove artifacts that are present in the ECG signal. So first in this is cancellation of 50 or 60 Hz interference in an ECG signal. In ECG recordings, one of the major problems is the appearance of an unwanted interference signal in the form of 60 Hz or 50 Hz in the output. While a number of techniques such as proper grounding and use of twisted pairs have been advocated for suppressing this interference, the another way of achieving the same is through the use of adaptive noise cancellation. So in this we will study about the adaptive noise cancellation, and the figure is shown in the next slide. As you can see, this is an adaptive noise canceller. The primary input to the filter is from the ECG preamplifier, while the reference input, that is the secondary input, is taken from the wall outlet with appropriate attenuation of the 60 Hz signal. The adaptive filter has two weights. They separately weight the two versions, that is one delayed by 90° and the other without any delay of the reference input, and sum to form the output of the filter, which is then subtracted from the primary input, that is the ECG signal interfered by the 60 Hz signal. The weights are varied in accordance with the tap weight adaptation equation of the least mean square, that is LMS algorithm. So you can see in this we are taking this reference input, and one is with delay of 90°, other is without any delay, and then we are using these tap weights which are represented in the form of W1 and W2, and we are using LMS algorithm to produce finally the output, that is minimization of error, or we can say that will remove the 60 Hz interference. So this figure we can see it enables the reference input to change both in magnitude and phase so that the integrating 60 Hz signal of ECG is effectively cancelled. Now in this figure, a typical result of the application of this adaptive interference canceller and how effective it has been in cancelling 60 Hz interference is shown. So you can see this is the primary input, then we have taken the reference input, and finally this is the noise canceller output. Now next is the cancellation of ECG signal from the electrical activity of the chest muscles. The importance of respiratory muscle functions in the pathophysiological features of the chronic obstructive pulmonary disease syndrome, that is COPDS, is highlighted. The prominent use of accessory inspiratory muscles, impaired motion of the diaphragm, asynchronous motion of the abdomen. Therefore, by placing surface electrodes on the external intercostal muscle, we can expect to obtain the electromyographic, that is EMG interference pattern for distinguishing between a normal subject and a patient with COPD. However, the acquisition of a clean, that is, free from interfering cardiac potentials is very difficult because of the generator activity of the heart. So, the removal of cardiac signals by simple and direct subtraction is not possible, as it is not feasible to obtain an identical copy of the cardiac activity that is corrupting the myoelectric activity because of the various non-linearities associated with the signal path and the recording. Also, the spectral analysis of the cardiac activity and myoelectric activity of the chest muscles indicate overlap of spectra between 1 and 5 Hz. Therefore, any type of linear filtering cannot be used. So in this, you can see we are using again a adaptive noise canceller. This is used to remove the interfering ECG activity from the recorded EMG. The assumption of no correlation between the contaminating and the contaminated signal is satisfied as the sources generating EMG and ECG are different or independent. The adaptive noise canceller had a transversal structure with ECG serving as the reference input and EMG as the primary input. The filter coefficients are adjusted using the LMS algorithm. So both the EMG and ECG signals were sampled at 500 Hz. The filter had 10 coefficients and step size of mu, which was chosen as 0.01. This was computed as by considering the maximum eigenvalue of the autocorrelation matrix of the ECG signal, that is the reference input to the filter. The step size was found to work satisfactorily with weights converging after 2000 iterations. So this process is done in mainly two stages. The first is the converged set of weights were obtained after the system had adapted a steady state, means we can say up till a steady state reached. Then these weights were used to process the new incoming signal. Now you can see this figure A shows the reference input to the noise canceller, that is the separately recorded ECG signal. Figure B shows the recorded EMG signal, and we can observe the negative peaks in the ECG signal. So figure C shows the filtered EMG signal relatively free of ECG, or we can say the noise interference. Now the next is cancellation of maternal ECG in fetal electrography, or we can say fetal ECG. In some applications, more than one reference input is required for effectively cancelling the interfering signal. In fetal monitoring, the abdominal electrocardiograms make possible to determine the fetal heart rate as also detect multiple fetuses. However, the quality of these waveforms is poor, making it very difficult to obtain a clear and clean assessment of the fetus ECG. This is because of the background noise, that is maybe due to the muscle activity and fetal motion, which often has an amplitude that is equal to or greater than the fetal heartbeat. Also, another serious problem is the interference from the mother's heartbeat, that in amplitude is 2 to 10 times greater than the fetus ECG amplitude. So here also the adaptive noise cancellation can be employed to obtain as far as possible a clean fetal ECG, so that not only the heartbeat rate but also the actual waveform of the electrical output could be observed. So the primary input to this adaptive filter in this case is through a single abdominal lead. The input contains both the maternal and fetus ECGs. So the reference input in this is more than one and is provided through four ordinary chest leads that record the mother's ECG. Figure gives the location of mother's and fetus cardiac electric vectors as well as the placement of leads to acquire the required electrical activity. You can see here in figure. So where in fetus and where at the mother's location we are keeping the electrodes to measure the ECG signals. Now each beat is terminated in a pair of electrodes. Both the chest and abdominal inputs were pre-filtered, digitized, and recorded on a tape. The chest lead provides the multiple reference inputs required for cancellation. Now this figure shows the multi-reference canceller. Each reference channel filter had 32 taps and the sampling frequency is chosen as 250 Hz. So you can see these are the multiple reference inputs. Now figure A shows the mother's heartbeat that is provided by one of the chest leads. Figure B shows the primary input as obtained from the abdominal lead. The dominance of the maternal heartbeat over that of fetus can be seen as you can see here. This is mother peak you can see and this is fetus peak. The noise canceller output is shown in figure C. The attenuation of the maternal ECG is clearly seen and also the preponderance of the fetus ECG signal. The effect of using different pre-filters for a bandwidth 0.3 to 75 Hz and a different sampling frequency of around 512 Hz on the performance of the filter was also carried out. The results are shown in this figure. So this is referred to as the wideband fetal ECG experiment. In this, figure A again shows the reference input. Figure B is the primary input from the abdominal lead and figure C is the noise canceller output. You can observe the baseline drift as well as the 60 Hz interference present in the primary input of the abdominal lead is reduced and the fetal heartbeat is hardly discernible in it. The reference input obtained from the chest leads is also affected by the 60 Hz power frequency. The output waveform shows that the maternal as well as the 60 Hz frequency are considerably reduced. Consequently, the fetal beat can be seen. Now we have another that is the cancellation of high frequency noise in electrosurgery. A device that is widely used in cutting tissue and coagulating blood vessels is the electrosurgical unit that is ESU. When it is used, it supplies a high frequency signal modulated at 120 Hz to the surgeon's knife and the power delivered is in the range of 100 to 200 watts. While it is in operation, the high frequency currents pass through the patient's tissue. These signals strongly interfere with the recording of the ECG signal. It is reported that these interferences are so strong that the signal to interference ratio that is SINR is approximately minus 90 decibels when that ECU is on. So conventional grounding, screening and other hardware techniques were unable to significantly improve this ratio. So Yilderman, Widrow et al. Have applied again the adaptive noise canceller to this problem. So you can see a block diagram showing ECU interference rejection system. And this is a detailed block diagram of the digital adaptive noise canceller. Again, we have primary input, reference input, and we have number of delays. Then we have tap weights. We are using this adaptive filter for that is based on LMS algorithm. And finally, we are producing the again analog output. So while the primary signal is taken from the chest electrodes, the reference signal is secured from a pair of electrodes placed on the arm in such a way that the interfering ECG should be minimum. Passive filters followed by active filters are used to remove frequency components that are above 60 Hz in both the channels. However, in this, the first three harmonics of the power line still remain in spite of the fact that the SNR of the ECG improved from minus 90 decibel to minus 10 decibel. So this figure shows adaptive noise cancelling with two reference inputs which is used to remove the interference. Now, what is the use of this dual reference? Dual reference was needed as there were two different interfering signals. One less than 25 Hz due to the variation of the RF current, and the other power line frequency 60 Hz and its harmonics. So the division between the two was affected using a digital low pass filter with a cutoff frequency of 25 Hz. Further, to improve the performance of the adaptive process, automatic gain controls were used both in the primary signal and the reference channels. The convergence parameters for the two different references was chosen between 0.02 and zero point 0.2 while the sampling rate was 400 Hz. So this figure shows the results of using the dual reference adaptive noise canceller. So you can see this power change, this where it is a power change. So this is all in this lecture. So for these topics, you can refer again the book by DC Reddy, that is Biomedical Signal Processing Principles and Techniques. So for now, thank you.